All right, in 9.3b, we're going to actually construct a confidence interval to estimate the difference between two means. So first of all, here's what the confidence interval formula looks like. And notice that it starts off with the difference of the two x bars, the sample means we got, plus or minus a t star, times the standard deviation that we talked about. Now notice it changed from a sigma to an s because it's from a sample, not the population. All right, to find t star, it's exactly the same way we found t star before, and I'll review you on that in a minute. Now, running the test itself, you're going to use a test and calculator. So you would go to stat test, and I want you to notice it's test number 0, okay? It's 0 right there, and it's the 2-sample t interval. Be careful that you don't pick the 2-sample t test. Then, just like before when we did means, it'll ask you, do you want to use the data in your calculator or do you want to use given statistics? So depending on the problem, you might need to use data. Or they gave you the statistics, the x bars and the sigma, or the standard deviations, and you have all that information, so then you can use the statistics option. So let's say you click on the statistics option. Notice you have to plug in the x bars, the s, and the n's. You have to plug in a confidence level. And now you're going to see this new line that says pooled, yes or no. Always click no on that. Okay, just always click no. And then you go down to calculate. So let's try one of these. All right, in many parts of the northern United States, two color variants of the eastern gray squirrel, gray and black, are found in the same habitat. A scientist studying squirrels in a large forest wonders if there's a difference in the sizes of the two color variants. He collects random samples of 40 squirrels of each color from a large forest and he weighs them. The 40 black squirrels have a mean of 20.3 ounces and a standard deviation of 2.1 ounces. The 40 gray squirrels have a mean weight of 19.2 ounces and a standard deviation of 1.9. Construct and interpret a 95% confidence interval for the difference in mean weight of the black and gray squirrels. All right. So I want to encourage you to highlight here, okay? 40 samples of each, that's pretty important. He has 40 black squirrels with a mean of 20.3 and a standard deviation of 2.1. So I'm going to use one color for that. And then for the 40 gray squirrels have a mean of 19.2 and 1.9 standard deviation. All right? Now, the other thing I want to highlight is what is the context? It's right here. For the difference in mean weight of black and gray squirrels. I'm going to need that when I state my parameters. Okay? Now, this is where it gets tedious on these two mean problems. Okay? So when we state a confidence interval, we want to estimate. It's really important to use estimate. So we say we want to estimate with 95% confidence, and I restate what's in purple here, difference in mean weight of black and gray squirrels. Right? Now, the plan step. In order to do the plan step, we have to say what is the test we're using, and we're using a 2-sample t interval, and then we got to check our two conditions. We got to see, is it random and is it normal? All right, so for random, I have to check that the 40 gray squirrels are random that he chose, black and gray. So I look back at my context because he collects random samples of 40 squirrels of each, so I know that. So I'd say simple random sample, n equals 40 black, and n equals 40 of the gray. So I've identified that both are random. For normal, I look at the sample size. It's 40, which is greater than 30, so I can use central limit theorem. So the black n is equal to 40, which is greater than or equal to 30. So because of central limit theorem, I'm good. And with the gray squirrels, n is equal to 40. It's greater than or equal to 30. So again, central limit theorem allows me to assume normality. Okay? So let's move on to the do step. Right. For the do step, remember our formula. It says x1 minus x2 plus or minus a t star times the s1 squared over n1 plus s2 squared over n2 all of that under a square root. All right, so let's take this in baby steps. Take our x1 and x2. So we're going to put that part in parentheses, like right here. So we're going to say 20.3 minus 19.2 plus or minus. Now t star, if you remember, when we did confidence intervals before, it's 95% here, so what's left over in the tail? So that's 0.025, right? So I'm going to use inverse t, and it's going to ask me the area of 0.025. And then I'm going to take the sample size and subtract 1. Now, if one of these samples was bigger than the other, you would take the smaller sample size. Okay? So this one is 40, so my degrees of freedom is 39. Okay? So if I do that, and I get a t star of 2.023. And then I'm going to fill in the formula. Okay? S1 was 20.3 squared over my sample size of 40, plus S2 was 1.9 squared over sample size of 40. Now, that part you got to show me, but remember the calculator is going to run the numbers for you. All right? So when I go into my calculator, I go to stat test. I need to go all the way down to two sample t intervals. So it's option 0. Hit enter, and they gave me the statistics, so I want to choose the statistics option. And I've already entered my data. Okay, there's x1, there's s1, n1, x bar 2, s2, n2. Now, if I keep scrolling down, it's going to ask me the confidence level. Adjust that as needed. And then you have the pooled. Always select no on pooled. Okay? And then hit calculate. And there's our confidence interval way up here. Okay? So it's 0.208 to 199. 1.992. There's my confidence interval. All right? Now, when we conclude, we start off like we did before we did confidence intervals. We can say we are 95% confident that the true difference in mean weight of black and gray squirrels is between 0.208 ounces and 1.99. All right? So that walks you through the state plan to conclude process. I mean, getting your feet wet today, a lot of little things, but none of which are very difficult. So hopefully that makes some sense, and we'll see you in